Hello everyone, this is Dwip CB, your trusted PCB partner. Today, our topic is how to separate and then connect analog ground and digital ground in a 6-layer board. Welcome back to the 6-layer board and signal revival course. In the previous video, we clarified the importance of separating analog ground and digital ground. But here's the problem. After all, they are part of the same system and ultimately need to be connected. So how can we separate them and then connect them in a way that suppresses noise while ensuring the system works properly? Today, we'll explain the only connection point between analog ground and digital ground and discuss grounding techniques for key components. Take this circuit as an example. On the left is the digital ground and on the right is the analog ground. How do we connect them? Let's take a look. Actually, it's right at this spot. There is a 0 ohm resistor and a capacitor here. Sometimes a ferrite bead can also be used. As you can see in the schematic, at this position you can choose a 0 ohm resistor, a ferrite bead, or even a common mode inductor depending on your actual needs. On a 6-layer board, effective separation of analog and digital grounds can be achieved in two main ways. The first is the physical partitioning method. On the intermediate plane, the analog and digital grounds are physically separated to form two independent regions. Then on the board, the analog circuit area and the digital circuit area are physically isolated. That is, as shown here, this entire area is for analog circuits and this side is for digital circuits. They are physically divided into two separate sections. What are the advantages of physical partitioning on a 6-layer board? You can split both the L2 and L5 layers at the same time, or use L2 as the digital ground and L5 as the analog ground, providing greater flexibility. The advantage is that the isolation effect is straightforward and it avoids direct contamination from digital circuits. The downside is that if high-speed digital signals cross the boundary between ground planes, their return paths will be blocked, leading to serious EMI and signal integrity issues. Therefore, unless you have professional experience, it is not recommended to casually split the ground planes. However, the purpose of our study here is to gain that professional experience. Now, looking at this drawback, it's clear that in this area, these equal length traces are obviously high-speed digital lines, and the upper line is the main air connection to the ADC's control line. So how do we solve the return path issue for these signals? Let's take a look. On the top layer, we did a left-right split. Looking at the AIRE second layer, ground zero, we see that this layer is not split. If we check its network, we can see that it uses digital ground D. Why do we do it this way? That's because the L2 layer needs to provide a return current reference for these high-speed digital signal traces that cross regions on the L1 layer to avoid reflections. Therefore, the L2 layer cannot be split. Now let's look at the L5 layer. The L5 layer is split again because in the inner layers there are no such high-speed digital traces crossing regions. This kind of split needs to be carefully controlled to ensure the reference plane for traces that cross regions. Second method is the single point grounding method, which unifies the ground plane. The main ground plane is not divided, and R2 and R5 are kept in a complete position. Instead, the digital circuit area and the analog circuit area are physically isolated locally. The respective Ds are connected to this unified complete D plane through the nearest connection hole. All digital and analog return currents flow to this complete D plane. The advantage of this method for a 6-layer board is that L2 and L5 can both be used as complete reference planes. L4 is used as a power plane so that the analog and digital connections each have an excellent reference plane. The advantage is that it avoids the risk of the middle section of the return path caused by the division of the ground plane. As long as the layout is reasonable, the risk will not spread. For most mixed analog designs, especially when high-speed digital and analog coexist, it is recommended to use a unified and complete ground plane and strictly distinguish it. However, this approach cannot achieve the best effect for analog because its digital D also comes over. It can only provide connectivity for analog D through wiring. It cannot provide a complete probe plane for analog D. Only we generally follow the first method, although the first method has higher requirements to ensure that there is a complete digital D-plane. It also ensures the integrity of the return entry of your high-speed input signal on the top layer. Where is the key connection point? Even with a single point grounding strategy, even if the ground plane is divided, the analog ground and the digital ground must ultimately be connected at a certain point to form a complete circuit. This connection point is crucial. Where is the ideal connection point? It is at the ADC or DAC chip. For ADCs and DACs, which serve as bridges for analog to digital conversion, their digital and analog signal processing intersect. Usually we choose the ADC or DAC chip itself as the sole connection point between the analog ground and the digital ground. The operation is to connect the ADC DAC analog ground to the PCB's analog ground plane and the digital ground to the digital plane. Then, the two independent planes are connected directly beneath the ADC DAC power supply through one or several main traces or vias. Other key connection points include power converters. If there are separate analog and digital power supplies, the ground of their power converters is usually a critical point connecting the analog and digital grounds. This needs to be handled according to the specific characteristics of the power converter. In our circuit, our chosen method for key grounding is to place a 0 ohm resistor and a capacitor in a certain area to connect the digital ground D and the analog ground D. We can also see that this position and this position are both supplied with dedicated analog power, providing isolated analog power supplies and thus separating the power for digital and analog sections. Grounding techniques to ensure both separation and connection start with layout as the top priority. Regardless of the grounding strategy, the most important thing is the layout. The analog and digital circuit areas must be physically and strictly separated, and wiring crossovers should be avoided as much as possible. As shown here, they are separated left and right, and only the necessary connection lines cross between regions. Filtering of the analog power supply. Even if the analog ground and digital ground are unified, strict LC filtering is still required for the analog power supply. Use DESR capacitors and magnetic beads to ensure the purity of the analog power, just like we use current limiting resistors and magnetic beads for the same purpose. Today we have delved into mixed systems on 6-layer boards and some strategies for separating and connecting analog and digital grounds. We have learned that whether it is physical separation or a unified ground plane, the key lies in noise suppression and current flow, and in choosing a single optimized connection point. Mastering these techniques will help you when designing complex mixed signal PCBs to effectively suppress interference and ensure high performance and reliability of your products. I hope this content can help you become an even better hardware engineer. If you enjoyed this video, please subscribe to my channel for more videos. Thank you, everyone.